Hello everyone, I'm Taisei Asai from Waseda University in Japan, and I'd like to thank you for giving me the chance to speak here today. And this research is a joint research with Dr. Tanaka and Dr. Sekine and Professor Oishi. And today I'd like to talk about the computer-assisted analysis for the bifurcation phenomena of the one-dimensional Hénon-type equation. First of all, I'll explain about the Hénon-type equation. We consider the one-dimensional Hénon-type equation, which is a boundary value problem like this. And there are three parameters in this equation. The parameter lambda is non-negative parameter, and the parameter L is a potential index, and the parameter P is a polytropic index. And now we know that if lambda equal to 0, the Hénon-type equation is the same as Hénon equation. And if parameter L equals to 0, the Hénon-type equation is the same as Md equation. Okay, and next, this is a background of the Hénon equation or Hénon-type equation. So, first, it was found that there are symmetric positive solutions in around the 1980s. And next, it was found that if parameter L is sufficiently large, then there are asymmetric positive solutions in 2000. And in recent years, the Hénon equation has been extended to the Hénon-type equation. This equation has the parameter lambda added like this, and for the study of bifurcation conditions. According to these studies, there are theorems for bifurcation phenomena. For example, this is a theorem about the bifurcation when the parameter lambda equals to 0 and P is fixed and the parameter L is moved. According to this theorem, if parameter L and P is satisfied like that condition, then there are some symmetric solutions. On the other hand, if parameter L is sufficiently small, then there is no asymmetric solutions, but there are some symmetric solutions. This is the bifurcation prediction. However, still only sufficient conditions for symmetric breaking bifurcation have been clarified. And the existence of multiple solutions near the bifurcation point and the structure of the bifurcation are not known completely. So this area is unknown. And next theorem. This is a theorem about the bifurcation when the parameter P and L are fixed and the parameter lambda is moved. And these are the conditions. And this is a branch prediction. But how many solutions exist in total before the bifurcation point lambda star is an open question, and this bifurcation structure and the bifurcation point are not known completely because in this theorem says that the solution the equation has at least 3 positive solutions. So we set the goals and the purposes. The goal of this study is solving unsolved problems like solution curves or bifurcations of the one-dimensional Hénon-type equation. And the purpose of this study is to verify the existence of multiple solutions of the Hénon-type equation near the bifurcation point and to track the bifurcation diagrams by computer assistance. Okay, now this is the notations of this study. We use LP function spaces or H10 spaces. And here we use embedding constants, which is satisfied like that inequality. When p equal to, we use the following optimal inequality like that in this domain. And if p equal not to, we use this theorem by citing this study. Okay, then this is a numerical verification method. First, we define the small f operator like that, and then we consider the following big form problem like this. And so, to conduct the numerical verification for this problem, we apply the Newton-Cantorich theorem. And next, this is a Newton-Cantorich theorem. If we can get such alpha and alpha beta is less than half, if alpha and alpha beta is less than half, then we can evaluate the error bound like that. And furthermore, the true solution U is unique in the closed ball with center approximate solution U hat and radial 2 alpha. And here, the constants alpha and beta are evaluated from above with like that. Therefore, these constants must be evaluated. The inverse operator norm is evaluated like that by citing this study, and the radial norm and Lipschitz constants are evaluated like that. In this Lipschitz constant, the maximum is unique to the Hénon-type equation. So in this case, the maximum equals to 1. Okay, and next. First, we consider the Hénon equation, like that equation, to compute area around the bifurcation points that was unsolved in theorem 1, like that prediction diagram. For effective solution verification, consideration of the singularity is necessary. Because the variable coefficient absolute x to the power of L on the right hand side of the Hénon equation makes the solution singular at the center of the domain. So for example, if we construct approximate solution with smooth weighted functions and integrate it numerically using like Gauss-Legendre quadrature, it is difficult to verify the solution only when L is an even number like 0 to 4, that point. So without effective verification of the solution near the bifurcation point, it is not possible to analyze the bifurcation point and the bifurcation branches. Okay, then we get the idea. To construct a basic function sequence with a singular function phi 0 and some basic functions sequences like that. We referred this study as a basis for this idea. And so specifically, we constructed approximate solutions as like that for. And more specifically, we defined the finite dimensional subspace of Bm of H10 as like this, and where phi n is defined by like that Legendre polynomials, and singular function phi 0 is defined like that. And we computed approximate solution to U hat by solving the matrix equation like that using the usual Newton's method. And this is a small notation, small remark. Since in this case, this inequality is satisfied, so the same constant Cm in this theorem can be used to evaluate the following problem like this. Okay, and next, implementation innovations. Since we need to calculate for the singular function like phi 0 like that, so we define a class that can host the exponential part like that A and the polynomial part like that Px at the same time. And we named the class FPSA, and the operations are defined as follows like that. In particularly about integration, in order to deal with algebraic type singularity, algebraic type singularity is also called power type singularity. This kind of integration is performed like this form. And next, in FPSA, we could not define addition between the different exponential parts, like that A, like this. So we define a class as like this by using a vector. So the class is named as PSA, and the operations are defined as follows like this. Okay. From the next page, numerical results. All computations were implemented the computing environment, and we used these toolboxes, KB library and interval. Therefore, the accuracy of all results was guaranteed mathematically. Okay, first, we mentioned the effect of singular basis functions. According to this table, if we mixed singular function, the residual norm is evaluated like that, and we verified this solution. But on the other hand, if we did not mix the singular function, the residual norm is evaluated like that, then the solution is not verified. And furthermore, if the result, the singular function phi 0 and increasing to the number of smooth basis functions to 100, the radial norm only drops to about 10 to the minus 4 order. So, the radials do not reach the order of the case with singular functions, this 10 to the minus 5 order. So the effect of the singular function is large. Okay, by the way, have we able to verify the solution in a previously unknown area, like that area? This is results. We were able to verify these solutions, uh, symmetric solutions or asymmetric solutions. And next, we consider the solving the solution branches. And then, in this case, we consider the verifying the solution branches by refers solution branches in this book. Then these constants must be evaluated. This is the results. We were able to verify these solution curves by verifying them on slightly shifted like that small intervals. Therefore, symmetric solution blue lines and asymmetric solutions orange lines are verified. Okay, next. We consider the solving the bifurcation point. To find the symmetric breaking bifurcation point of this problem for parameter L, first we set VS be a symmetric subspace of H10, and we consider the solving this simultaneous equation to obtain the bifurcation point like this. And then we define the solution bold U, which is included symmetric solution and asymmetric solution phi and parameter f. And we consider this problem. The numerical verification method performed for this problem by Newton-Kantorowicz theorem. Then, so the constants must be evaluated. Inverse operator norm is evaluated like that by citing these studies, and residual norm and Lipschitz constants is evaluated like this. Okay, then. This is a small note. When generating Jacobi matrices to solve the bifurcation point, we need to over the form like this term. So we added a new element for integration in order to deal with algebraic type singularity like that absolute part and the log type singularity that is log. And the integration is performed like that. Okay, and this is a result. We got the approximate bifurcation point L hat like that, and the error bound is evaluated like that. So the true bifurcation point L exists in the interval like this. So like that, red point bifurcation point is verified. Okay, next. We consider the Hénon-type equation to compute the area around the bifurcation point that was solved in theorem 2. In this theorem, the parameter P and L is fixed, and the parameter lambda is moved like that. And in this study, in this Tanaka's study, this is branch prediction diagram. Okay, this is our result. According to this solution curve, there are some turning points and bifurcation breaking point, and particularly in around this area, there are 7 multiple solutions. And we verified like that 7 multiple solutions when the parameter lambda is fixed like that. And all multiple solutions are verified. Okay, and next, we consider the findings and turning point of the symmetric solution. So we set solution spaces like that, and we consider the solving this simultaneously equation to obtain the turning point, and we consider the following problem like that. The numerical verification methods are performed for this problem. As with the calculation of symmetry breaking bifurcation point, it can be verified numerically by evaluating these constants and using Newton-Kantorovich theorems. And this is a remark. When we consider to find the turning point of asymmetric solution, we set the solution space to be like that, bold B equals to like that, with the BA be an asymmetric subspace of H10. And then this is a result. When we fixed P and L like that, and then approximate turning points evaluated like that, and the true turning points exist in these intervals. So on this lambda 1 and lambda 2 and lambda 3 turning points are verified. Okay, finally, this is a conclusion and future work. In conclusion, when we fixed parameters lambda and p and moved the parameter L, then the effect of singular function has succeeded to reduce the residuals even with few basic functions. And the bifurcation branches and bifurcation point were proved by computer-assisted proofs with efficient numerical verification method. And when we fixed parameter L and P and moved the parameter lambda, we found that unexpected 7 multiple solutions, and its structure is verified. Therefore, we obtained the results that complement the theoretical analysis in this study. In future work, we want to track the bifurcation diagrams when the parameter L and lambda are moved simultaneously, and we would like to deal with the Hénon-type equation extended to multiple dimensions. Okay, this is references. Thank you for listening.